Hi everyone, welcome to my presentation on the transportation of mercury in the Amazon River. My name is Felix Canari and this is for the class Engineering 416 Transport Phenomena. Located in South America, the Amazon River is one of the largest rivers in the world. In recent years, there have been small-scale artisanal gold mining operations, or ASGMs. A major byproduct of ASGM is elevated levels of mercury in the atmosphere and by and adverse and due to that higher levels of concentration in the water columns. The concentration of mercury being transported, it directly affects the health of the individuals in the area since they consume mostly fish, and this fish has bioaccumulated enough mercury to be harmful for these individuals who have high fish diets. The concentration of mercury measured along the area we will be studying is 0.5 nanograms per liter on average. The goal of this presentation is to see at what distance mercury concentration reaches zero point 0.5 nanograms per liter along this section of the Amazon River. This will tell us more about the behavior of the river and our contaminant for future studies. We've chosen zero point 0.5 nanograms per liter based off the observation that at this current level, it causes enough bioaccumulation in the fish to cause problems for the individuals around. The EPA states a much higher level of mercury for consumption of water. However, we're not looking at the consumption of water in the water column. We're looking at the effects that mercury has on the wildlife in the water, and a byproduct of that is the health of the individuals in the area. When observing mercury being transported down the Amazon River, we can assume it's a continuous release. This is because mercury is released into the atmosphere and it it clumps together with water vapor, and when water vapor condenses and rains, mercury rains along with it, creating runoff into tributaries that lead into the Amazon River. So it is continuous. The Amazon River is 20 meters deep, 4.5 kilometers wide on average, and the observed length we're going to be looking at here is about 1,000 kilometers. The velocity of the river is 2.16 meters per second on average in this length that we've looked at. The mathematics for this plume type, um, when we take our time scale we're looking at, or if we take the length of the river and divide it by our velocity, we get our peak concentration time at 5.4 days. Um, when we look at our vertical and lateral mixing time, we see that in our vertical column, we have a mixing time of 180 seconds. This is much less than 5 days, so we are well mixed in our vertical column. As for our lateral mixing time, that is around 351 days. This is definitely more than our peak concentration time, meaning we are not well mixed in our lateral direction. Finally, using what we've gathered, we can calculate our Peclet number, and we've got a Peclet number of 4.2 times 10 to the power 6. This means that we are greater than 1, which means that our plume type is diffusus dominated. Because we are not well mixed in 2 dimensions, we can assume that this is a line source. So some assumptions we can make about our PDE are that it is steady state. The reason for this is if we look at the hydrograph on the left, hydrograph letter B, we can see that the precipitation climatology graph, or the hydrograph, it is changing month to month. And if we look at each month, we see that there's a noticeable change of slope. However, our time scale that we're looking at is roughly 5.4 days. So if we look at a time scale of 5.4 days on this hydrograph, there's little to no change in slope. Therefore, the flow can be considered steady. The Amazon River, given the parcel, we can assume that sorption is also occurring at the lateral banks. The sorption occurring on the lateral banks can be considered perfect sorbing banks due to how long our river is. Because they are perfectly sorbing, this means we'll have Dirichlet boundary conditions there. For our decay constant, Mercury does have a decay constant, but is highly negligible because of how dense Mercury is and how it's a heavy metal. The mathematics behind our PDE are given above. Given our assumption, we write out our boundary conditions as well as our initial conditions. The governing equation is for our continuous release steady state on an infinite domain for a line source. The approach that we will be using is we will be using the solution to our PDE from the last slide. Our solution is given right here. With the solution, we can determine our longitudinal position. Um, so for this general form, we have everything we need um, except our longitudinal position x. So we will be solving for x using bisection. Here are the unknowns and knowns of our solution to the continuous steady state release on an infinite domain line source. We know our velocity, our diffusivity in the y direction, as well as our height, our m dot, and our decay constant, as well as our initial position for both y and x. As I stated before, the unknowns is our position where we will experience the peak concentration. We will use bisection to solve for this. Using bisection, we get that peak concentration is expected at the length of 332 kilometers along our section of river. Now that we have our peak concentration along with everything else, we can then visualize our plume. To the right is a graph visualizing our plume. The y-axis is our lateral distance, the x-axis is our downstream distance, and the gradient colors is our concentration. Towards the very ends, towards each lateral distance, towards 4 and -4, we see that there are no concentration, showing our perfect sorbing boundaries, and we see peak concentration as highlighted as yellow, being the highest at around 330 kilometers downstream. As we move downstream, peak concentration goes down. This is due to our diffusivity as well as our very low decay coefficient. Given more time and instrumentation, I would use a different language, perhaps C++, due to its better handling capabilities and less reliance on RAM. The model previously shown we used Python does not take into account real sorption or the settling of mercury in the river. It does not also take into account the change of precipitation over a year. That brings us to the next thing. Um, I would also consider looking at a longer time frame to see how mercury behaves through the course of the year. This would make my model unsteady since we will be looking at the entire course of that hydrograph, which has a changing slope, varying slope throughout the year. As far as literature goes, there's not too much recent research done in this area. This is due to the high cost and resource extensive it is to collect data along that section of the river. Getting to that part of the river is not only hard, resource extensive, but not a lot of people have that resources. Where people do data collect, uh, it is often collected at places of residencies or small towns, so not really realistic. We're not getting a good pool of data. We're getting convenient data that is collected at these spots. Thank you for coming to my presentation, and yep.